now. So.
Okay, so thank you for the invitation to give this talk. So this is joint work with Giovanni Valente from the Politecnico di Milano. And this paper is going to appear in this new volume on scientific realism, edited by Lyons and Vickers, which I think is going to be published in the next weeks or so. So it's forthcoming there in case you want to take a look at the volume and at the paper. In this talk and in the paper in general, there is one main question. And the question is whether infinite limits are compatible with scientific realism. So I assume that most of you, if not all of you, are familiar with scientific realism. But as you know, there are different versions of scientific realism. So it's important that I start by making clear what I mean by scientific realism here. So what I take scientific realism to be here is this traditional idea that our best scientific theories regarding observables and non-observables are true, or at least approximately true. So as you know, the main argument in favor of this scientific realist idea is the no miracle argument that says that the success of our best established theories would be a miracle if the theories wouldn't be true. And the notion of approximate truth here is very important because we are not committing to the idea that our best theories are literally truth. We are just saying that they need to be at least approximately true. And in particular, the version of scientific realism that is more compatible with what I will defend is explanatorianism, which says that we need to commit ontologically at least to those parts of the theory that are essential for giving an explanation of certain phenomena. So I will not speak from the perspective of entity realism or structural realism, but we can discuss potential applications to these other views of realism in the Q&A. So that's all what I will say about scientific realism in particular. So now let's move to infinite limits. So infinite limits are limits in which a parameter, in general a physical parameter, goes to infinity. That parameter can be, for example, the number of particles, or it can be time. And the use of infinite limits is widespread in physics. You find infinite limits in theories ranging from thermodynamics and statistical mechanics to quantum field theory, quantum gravity, and black hole physics. And there are some cases in which the use of infinite limits doesn't seem to be just pragmatic. So it doesn't seem to be just for the purpose of making calculations easier, but there are some cases in which the use of the infinite limits seem to be essential to give an explanation of the phenomenon, and therefore essential to recover empirically correct results. So this use of infinite limits, in particular when the limits seem to be essential for given explanation of the phenomenon, are very puzzling from a realistic perspective, because when we look at the world, we think that real systems are finite. For example, we don't believe that in this glass of water, there are infinite number of particles. And apart from that, the finiteness of real systems is assumed by very well established theories like the atomic theory of matter, for example. So this use of infinite limits raises different questions for the scientific realist. One of these questions is, how can we explain the empirical success of models that introduce such an unrealistic assumption like an infinite limit? And the second question is, to what extent these models that use infinite limits are compatible with scientific realism? So what I will do today is try to give an answer to these two questions. And for that, I will offer a general formulation of what I call the paradox of infinite limits. And I will also try to build a taxonomy of different uses of infinite limits. And this taxonomy is going to help me to answer this question, hopefully in a very systematic way. So that's the idea. And this is the plan of the talk. It's very ambitious, as I said at the beginning, but I will try to go through all points. So let us start by the taxonomy of infinite limits. So in order to built a taxonomy for infinite limits in which we distinguish different uses of infinite limits, I think it's very important to distinguish between different types of misrepresentations of the target system in our scientific theories. John Norton in 2012 distinguishes between idealizations and approximations, and Gottfried Smith distinguishes between idealizations and abstractions. And what we do here is to combine these two approaches and to distinguish between idealizations, approximations, and abstractions. So idealizations, according to Norton and Gottfried Smith, are fictional systems or imaginary systems whose properties resemble the properties of some real-world target systems. In some cases, these fictional systems have properties that approximate the properties of real-world target systems. Approximations, on the other hand, are inexact descriptions of the target system in terms of propositions, and they don't need to make a reference to an idealized system or an imaginary system. So this means that one can have approximations here without idealizations, which would be cases in which we give an inexact description of the target system without invoking a fictional system. And there is a last case of abstractions, which is the omission of some relevant features without misrepresenting the properties that make a difference for the phenomenon that we want to describe. So why is it important to distinguish between these different types of inaccurate representations? Because we are going to defend that infinite limits can be used as idealizations, as approximations, or as abstractions. But in order to build that taxonomy, we need another distinction that comes from Jeremy Butterfield, which is a distinction between different limits. And this is the technical apparatus that we need for the taxonomy. So Jeremy Butterfield distinguishes between taking the limit of a system, taking the limit of a sequence of functions, and taking the limit of the values of the sequence of functions. What is taking the limit of a system? So imagine that Sn represents a system characterized by some physical parameter n, which is the parameter that goes to infinity, which can take on discrete or continuous values. If n represents the number of particles in a gas, then n will take discrete values, of course. And if n represents time, for example, n will represent continuous values. As n grows, as n goes to infinity, one can define the sequence of systems. And the limit of this sequence of systems is going to correspond to an infinite system. And according to the classification that I gave before, this infinite system can be interpreted as an infinite idealization, right? Because we postulate the existence of this infinite fictional system. But one can also take the limit of a sequence of functions. Consider that the function f represents a physical quantity of interest like volume or magnetization. So one can define a sequence of functions as n, the parameter that goes to infinity, grows. The limit of this sequence of functions is going to be the last element of the sequence and is not necessarily associated with the existence of the limit system, which means that the limit of the sequence of functions can be different from the function that is associated with the limit system. So this is very important because in some cases, these two limits, the limit of the sequence of functions and the function associated with the limit system, coincide, but in some other cases that they don't coincide. And that's going to play an important role in how we justify the use of infinite limits from the perspective of the realist. So the last type of limit that we can take is the limit of a sequence of values. So here we do the same as before, but we define a series of values that are evaluated according to certain function. And this series, this series will converge when we take the parameter n to infinity. So taking the limit of a sequence of values is very important in order to test the empirical correctness or empirical adequacy of our models. And as in the first case, we can distinguish between the limit of the sequence of values of the function and the value of the quantities evaluated in the limit system. And again, this is going to play an important role when we distinguish between different types of different uses of infinite limits. So now we can finally build this taxonomy. We can use limits as approximations without idealizations, where two, that means the limit system, is not well defined or it doesn't give us empirically adequate results, and one, that is the limit of the sequence of functions, is well defined and give us empirically correct results. So this is a case in which, in Norton's words, approximations cannot be promoted to idealizations because the infinite system doesn't exist or it doesn't give us empirically correct results. The second case are idealizations yielding approximations. These are cases in which the two limits that I mentioned before are well defined and equal, and both are empirically correct. So in these cases, one can straightforwardly interpret the idealization, that means the infinite system, as giving us an approximation of finite systems when n is large but finite. And there is another case, which is the most controversial case of essential idealizations, in which 1 and 2, so the two limits that I defined before, are well defined, but they are not equal. And it is rather 2 than 1, the one that is empirically correct. So it is rather the infinite system than the sequence of functions, the one that is empirically correct. So of course, the most mysterious case and the most controversial case from the perspective of the realist, because in this case, one cannot, it seems that the only way of recovering empirically correct results is by invoking this infinite system, this infinite idealization. And I will say, of course, more about this in the rest of the talk. And to this taxonomy, one can add the case of infinite limits as abstractions, which I will mention by the end of this talk. These infinite limits as abstractions don't fit with the formal setting that I explained before, but we can define infinite limits as abstractions as cases in which the parameter n doesn't represent any physical parameter of the target system. And I'm going to give an example, as I said, by the end of this talk. So now that I have built this taxonomy of different uses of infinite limits, I would like to explain what I call the paradox of infinite limits. So as some of you know, infinite limits have been very controversial in the philosophy of science literature. And for some philosophers, infinite limits lead the realist to a paradox. So this paradox of infinite limits has been formulated focusing on particular case studies, for example, the case of phase transitions. But I think that this paradox can be formulated more generally. So for all uses of infinite limits. And this would be the general formulation of the paradox of infinite limits. So the paradox of infinite limits would arise as a contradiction between the following three statements. The first statement is the finiteness of real systems, which is the idea that we assume that real systems are finite. As I said, that is consistent with our experience. We don't observe infinite processes, we observe finite processes. And that is also consistent with well-established scientific theories. The second claim is the indispensability of the limit system. So here is, this is the assumption that in some cases, the explanation of a phenomenon can only be given by means of claims about an infinite system. And it seems that we cannot explain that phenomenon, or we cannot recover empirically correct results if we don't appeal to this infinite system or infinite idealization. And the third statement is what Baker called the enhanced indispensability argument, which says that if a claim or an idealization plays an indispensable role in the explanation of a phenomenon, then we have to believe in its existence. So as you see, it seems that we cannot hold the three statements without falling into a contradiction. So the question is, how can we solve this paradox? And I think the way of solving this paradox depends on the use of the infinite limit. For example, in the case of approximations without idealizations, the paradox doesn't even arise because we don't have statement true. So statement true doesn't hold. These are cases, just to remind you, in either or it doesn't recover empirically correct results. So these are not cases in which the infinite idealization appears to be indispensable for the explanation. So we can solve this paradox by giving up statement two in a very straightforward way. So these are cases then in which we use infinite limits just as approximations without invoking any fictional system and therefore without appealing to any idealization. The question is, which are cases or which are good examples of approximations without idealizations? Here, there is no consensus among philosophers. John Norton, for example, thinks that phase transitions and reversible processes are cases of approximations without idealizations, but many philosophers would disagree with that. So I believe a less controversial example of approximation without idealization can be found in special relativity. So as you know, the quantities of special relativity are defined in terms of the Lorentz factor, and one can recover the classical quantities from the relativistic quantities by taking the Newtonian limit, which is, well, V over C squared going to 0. Even if in principle there are different ways of interpreting this limit, it seems that the most plausible way of interpreting this limit is just as an approximation of velocities that are very small compared to the speed of light. It seems implausible to interpret this limit as the speed of light going actually to infinity, because that will imply that the energy of these bodies is also infinite, and that would not give us an empirically correct representation of realistic systems. And this can be even more easily seen by the fact that the Lorentz factor can be expressed as a Taylor expansion. So it seems like a very straightforward approximation. What is interesting here is that in this case, one can even have a clear notion of approximate truth, in the sense that we can quantify the degree of misrepresentation in our scientific models by considering how many terms of this series expansion have been taken into account. So if we take just the first term, we will have an approximation of more realistic models, but maybe not a very good approximation. If we take more terms, we will have a more realistic representation. So this use of infinite limits as approximations without idealization seems very uncontroversial. And something similar happens when we use infinite limits as idealizations yielding approximations, which are cases in which the two limits that I mentioned before coincide, and they both give us empirically adequate results. So informally, in these cases, since the two limits coincide, one can straightforwardly interpret the idealization as an approximation of finite systems when the parameter n that goes to infinity is very large but finite. A little bit more formally, in these cases, one can show that as n goes to infinity, for some finite value n0 characterizing a target system, the value of the function evaluated in the finite system approximates the value of the functions evaluated in the infinite systems, in the sense that there is an arbitrary real epsilon bigger than 0, such that the difference between the value of the function evaluated in the finite system and the value of the function evaluated in the infinite system is smaller than an epsilon. If we assume that this epsilon is small, then if the infinite system give us empirically correct results, then we can conclude that the finite system will also give us empirically correct results, which means that the infinite idealization is not essential for recovering empirically correct results, and therefore that we can dispense from the infinite idealization. So in this case, as in the previous case, one can straightforwardly solve the paradox by rejecting statement 2, which speaks about the indispensability of the limit system. An example of this, although I will not explain it in detail, can be the the idea of reversible processes in thermodynamics. So reversible processes in thermodynamics are represented as a continuous line. And in order to give a representation of reversible processes in thermodynamics as a continuous line, one needs to assume that reversible processes occur infinitely slow, which implies taking the infinite time limit. So there are good arguments suggesting that these reversible processes, or more technically reversible quasi-processes, can be interpreted as an approximation of irreversible processes happening not infinitely slow, but very slow. And in this case, again, there is a notion of approximate truth because in principle, we can quantify the difference between the values of the quantities evaluated for finite processes and the values of the quantities evaluated for infinite processes. Just as a caveat, John Norton would disagree with me on this because he thinks that reversible processes are cases of approximations without idealization. But Giovanni Valente has a paper where he replies to John Norton, and since I co-authored this paper with Giovanni Valente, we trust Giovanni Valente here. But you might disagree with us. The thing is that independently of whether you interpret reversible processes as cases of idealizations yielding approximations or approximations without idealizations, you can solve the paradox in this case by rejecting statement 2.
Could you tell us why Norton thinks that?
Because he thinks that reversible processes have a paradoxical character. So he thinks that you cannot actually build these reversible processes as a fictional system without falling into paradoxes on the heat exchange. So basically, the reply that Giovanni gives is that one shouldn't consider reversible processes as real processes, but as a quasi-processes, which are mathematical constructions. And that's why we can still consider them as idealizations, but not in the sense of real processes that are idealized, but in the sense of mathematical processes that are idealized. That's more or less how the discussion goes. But the thing is that in either case, you have idealizations yielding approximations or approximations without idealizations, and you don't fall into the paradox, or you can solve the paradox rejecting statement 2. Good, so to sum up what I have said until now, it seems that in the case of infinite idealizations yielding approximations and limits as approximations without idealizations, we can solve the paradox by rejecting statement 2. And moreover, one can see that in both cases, if we define a topology, then we can have a nice definition of approximate truth, which would mean that infinite limits used in this sense are not only uncontroversial for a realistic perspective, but they have also certain advantages with respect to other idealizations, because in this case, you can have a clearer notion of approximate truth, which is always very hard to define when we talk about idealizations in general. So now let us move to the controversial case, which is essential idealizations, as I anticipated. So as I said, essential idealizations are cases in which the limit of the sequence of values doesn't coincide with the value of the quantities evaluated in the limit system. And it is rather the second than the first, the one that is empirically correct. So it seems that we can only recover empirically correct results by invoking an infinite system, which is a fictional system, right? So in a sense, it seems infinite idealizations here seem indispensable, because it seems that we cannot recover empirically correct results by invoking a finite system. It seems that we need the infinite system in order to give an explanation of the phenomenon and to recover the correct results. These have been called in the literature cases of singular limits. Bateman, for example, speaks about cases of singular limits, and also Michael Barry. Let's see now a candidate example of essential idealizations. This is the most important example, I think, or at least it was the example that started this discussion on infinite idealizations in science, at least in the current debate. And this is the case of first order phase transitions. So first transitions, for the ones that don't know, are these sudden changes in the phenomenological properties of a system that one observes, for example, when liquid water turns into vapor. And why the first order phase transitions have been considered to be a case of essential idealization? Well, because in thermodynamics, one defines phase transitions in terms of discontinuities or jumps in the derivatives of the free energy. An example of a quantity that displays a discontinuity in the liquid-gas transition is volume. The problem is that in statistical mechanics, the free energy is defined as the logarithm of the partition function. And the partition function is a sum of analytic functions that cannot display a discontinuity unless we take the thermodynamic limit, which means that it seems that the only way of recovering discontinuities, which is supposed to be the empirically adequate description of phase transitions, is by invoking the thermodynamic limit, whereby n, the number of particles, and the volume go to infinity. So this appears to be a case of essential idealization because it seems that the only way of explaining a phase transition and the only way of recovering empirically correct results is by taking the thermodynamic limit. So in these cases of essential idealizations, the solution of the paradox is a little bit less straightforward than in other cases, because it seems that we cannot so straightforwardly give up statement 2, which is the indispensability of the limit system. So what can we do? Different proposals have been suggested in the literature. As you see, there are philosophers that reject statement 1, philosophers that reject statement 3, and philosophers that reject statement 2. Today, I will suggest that the most plausible solution is to reject still statement 2, but before I want to comment on the other possible strategies, which is rejecting statement 1 and statement 3. So statement 1 is the statement about the finiteness of real systems. There are not so many philosophers who are ready to give up the finiteness of real system, because, as I said, intuition tells us and experience tells us that real systems are finite. And this is also consistent with very successful theories like the atomic theory of matter. But there are some philosophers who have opted to solve this paradox by trying to reject statement 1. And one of them is Liu. So he very recently in that special issue that Karim was advertising, suggested that we can reject statement 1 by adopting contextual realism, which is, well, a very sort of revisionary, if I can say, way of modifying scientific realism. So he says that if one adopts contextual realism, which is the idea that claims are false or true only relative to some background theory, then we can say, with respect to condensed matter physics, that the claim that real systems are infinite is true. So that claim real systems are infinite is true with respect to condensed matter physics. Of course, if our background theory is the atomic theory of matter, then that statement that real systems are infinite would be false. But we can still hold that this claim is true if the background theory that we have in mind is condensed matter physics. So I believe that this strategy is fine if you want to accept contextual realism, but it's not good if you want to endorse other forms of realism. The other option that has been suggested is to reject statement 3. So this is the enhanced indispensability argument that says that we should commit ontologically at least to the parts of the theories that are essential for an explanation of certain phenomena. So Baron also in that special issue in 2019 suggested that we can give up to statement 3 by distinguishing between constructive indispensability and substantive indispensability. Constructive indispensability means that there is reason to believe that an entity or an idealization can be dispensed, but we don't know how to do it now. And substantive indispensability is when there is no reason to suppose that such an entity or an idealization can ever be dispensed. So he says that constructive indispensability doesn't commit us or doesn't lead us to commit to the to commit ontologically with the claim that is constructive indispensable, whereas substantive indispensability lead us to commit ontologically to the idealization. So for him, constructive indispensability is not harmful for scientific realism, whereas substantive indispensability it is. So now the question is, how can we distinguish between constructive indispensability and substantive indispensability? And here he suggests a test of coherence. So he says that if a claim is not consistent with other accepted theories, then it is only constructively indispensable. And he addresses the case of phase transitions. And he says that since the existence of infinite systems is not consistent with the atomic theory of matter, then we shouldn't take that idealization seriously, which would mean that that idealization is only constructively indispensable. So I think this is sort of plausible, but it seems to beg the question, because what we want to do here is to explain the apparent contradiction between well-established theories and the need for certain idealization. So we would like to do something more here. Another proposal that also attempts to reject statement 3 was suggested by Eli Czech. So he suggested that we should not commit ontologically to infinite systems because infinite systems are no more than mathematical objects. I think this is fine, maybe from an empiricist perspective or instrumentalist perspective, but maybe the realist would not be very satisfied with this solution, because as Czech himself recognized, the realist is interested in our abstract scientific accounts getting something right about the world. So this also doesn't seem to be very satisfactory from a realistic point of view. So it seems that the only solution that we have, again, is try to reject statement 2, which is the statement that speaks about the indispensability of the limit system. And this is precisely the strategy that Jeremy Butterfield defended in 2011, when he focused on the case of phase transitions mostly. So the solution that he offers to the paradox, although he didn't have exactly this paradox in mind, was twofold. First of all, he said, we need to distinguish which are the relevant quantities here in the case study. And second, once we distinguish which are the relevant quantities, we are going to see that the behavior of these quantities in the limit is an approximation of the behavior of the quantities on the way to the limit. So if we focus, once we distinguish what are the relevant quantities of the system, we will see that these quantities converge smoothly to the limit. And how did he defend that claim? By using a toy example, which is a toy model, which is a very, very nice toy model. So he considered this following sequence of functions that you see here. As you can see, as n goes to infinity in this sequence of functions, the sequence of functions will converge to this discontinuous function, which is discontinuous at point x equals 0. But even if the limit function is discontinuous, this is not a case of a singular limit, because the sequence of functions will converge pointwise and smoothly to this discontinuous function. Now one can define another function, which we will call f, that takes values depending on the function g. For example, takes value 1 if g is continuous, and takes value 0 if g is discontinuous. If we focus on the second order function here, then we will think that the values of g when g is continuous are very different from the values of g when g is discontinuous. And he thinks that this is exactly the problem that people are making, or the mistake that people are making in the case of first order phase transition. they are focusing on a second order function instead of focusing on the thermodynamic function, which is the relevant function, the relevant quantity. And he says he considers the case of first order phase transition in a magnet at low temperature. And he says that if we focus on the magnetization function, then we will see that the magnetization function acts exactly like this G function here, and that converges smoothly to the discontinuous function at the limit. So once we know in which quantities we have to focus, then we can solve the mystery, and we will see that the behavior of the limit at the limit is just an approximation of the behavior on the way to the limit, or the behavior when the parameter n is very large but finite. Now the question, so this is a very nice solution that I really like personally. The question is, how general is this solution? And some philosophers have asked precisely this question and have studied other cases different from first order phase transition. In a case that have called a lot of attention in the philosophical literature is the case of spontaneous symmetry breaking. Fraser, Landsman, and Wallace, for example, analyzed spontaneous symmetry breaking, different types of spontaneous symmetry breaking. And they conclude that even if in these cases, one can give a deflationary interpretation of the thermodynamic limit, this deflationary interpretation is much less straightforward than what Jeremy Waterfield suggested. So here it's not about focusing on the right quantities and observing that these quantities converge. What sometimes this implies is that one needs to revise the definition of spontaneous symmetry breaking in order to give a deflationary interpretation of the limit. So I will not delve into this case study, but we can discuss it in the Q&A. Fraser, for example, suggested that in the case of spontaneous symmetry breaking, we need to relax the assumptions that allow us to define spontaneous symmetry breaking, like the assumption that only one of the minima is actually realized, or the assumption that the symmetry breaking is actually spontaneous. And this second strategy is in line also with what Landsman suggested, that symmetry breaking in finite system can be the result of very small perturbations coming from the environment. But as I said, this is a very complicated example, so we can discuss it in more detail in the Q&A. I will now skip it, because what we can learn from this then seems that there can be deflationary interpretations of the thermodynamic limit, but these deflationary interpretations seem to depend on the case study. So for quoting Fisher, there doesn't seem to be a standard recipe to give a deflationary interpretation of the limit. Another question is whether such a deflationary interpretation can be given to other interesting cases of spontaneous symmetry breaking, like the Higgs boson or the existence of quantum phase transitions. It seems that this again need to be answered on a case-by-case basis, and I don't think we are at the stage now of thinking that we have given a deflationary interpretation of all possible cases of essential idealizations in physics. So the moral of this part is that it seems that the most plausible solution to solve the paradox, even in the case of essential idealization, which is also realism friendly, is to consist in giving a deflationary interpretation of the infinite idealization. Since by giving a deflationary interpretation of the infinite idealization, we are saying that the infinite idealization is not indispensable to explain a phenomenon or to recover empirically correct results. This implies a rejection of the statement 2 of the paradox of infinite limits. Whether this can be done and how this can be done, I think depends on empirical research and should be decided on a case-by-case basis. So to say it again, I don't think there is a standard recipe to give the deflationary interpretation of limits. And now if I have time, so in the last 5 minutes, I will go to the last part that I promised at the beginning, to the use of infinite limits as abstractions. So before I talk about infinite limits as abstractions, I will say a little bit more about abstractions. I said that abstractions are cases in which we omit irrelevant details, but we give a literal or very accurate description of the factors that make a difference for the phenomenon. Abstractions in the philosophical literature have been considered as harmless for scientific realism, especially because they don't involve a misrepresentation with respect to the quantities that make a difference for the phenomenon. Still, Chakravarti, for example, says that in the case of abstractions, we don't have just pure truth, we do have a notion of approximate truth. But the notion of approximate truth is different from the notion of approximate truth that we have in cases of idealizations or approximations. And he gives a very nice definition of approximate truth qua abstractions, where he says that the greater the number of factors built into the representation, the greater its approximate truth, which, as you see, is different from cases of approximate truth in abstractions or approximation. And now I think a nice example of the use of infinite limits as abstractions is renormalization group methods. Again, I don't have time to describe renormalization group methods in detail, but renormalization group methods are methods that have been used to explain continuous phase transitions, and in particular to explain a phenomenon of universality, which is when, I think you're mostly familiar with this, is when different systems behave in the same way qualitatively and quantitatively close to the critical point. So in this framework, after one takes the thermodynamic limit, what one does is to define a transformation that coarse-grains the system. And one applies this transformation infinitely many times until one arrives at a fixed point. Since one applies the transformation infinitely many times, the number of iterations of the renormalization group transformation can be considered as a limit, as an infinite limit, in which the parameter doesn't represent a physical parameter. And this case, I believe, can be interpreted as an abstraction, like as an infinite abstraction, because at each step, at each coarse-graining procedure, we are getting rid of the irrelevant coupling constants. So it seems that we apply an abstraction procedure here infinitely many times. Bob Batterman didn't explicitly speak about renormalization group methods in this sense, but he says that this new renormalization group theory of critical phenomena reflects a different conception of the role of asymptotics and infinities. And I agree with him in this sense. I think the use of infinite limits here seems to be very different from other uses of infinite limits. But as I said before, abstractions seem to be uncontroversial for realism. So then why should they cause a problem? But interestingly, the use of renormalization group methods have been considered as one of the most paradigmatic examples of essential idealizations in physics. And this is why. So Bob Batterman, for example, says, if we want to explain universal behavior of finite but large systems using renormalization group methods, then we need to find a fixed point, and to my knowledge, this requires an infinite system. So it seems that the fixed point here requires assuming an infinite system in the first place. So this whole framework seems to rely on an infinite idealization. That, according to Batterman, is necessary to recover empirically correct results and to give an explanation of universality. But a few years ago, I published a paper in which I tried to give a deflationary interpretation of the two limits involved in the renormalization group framework. I will not go into details of this, but I will summarize this argument. So I said that in the case of continuous phase transitions, one first has to realize that there are at least two infinite limits involved. One is the thermodynamic limit that can be interpreted as an infinite idealization, and the other is the infinite iteration limit, which should be interpreted, as I said now, as an infinite abstraction. Second thing that one needs to realize is that these two limits don't commute, which means that one has to take the thermodynamic limit before taking the infinite iteration limit. And once one realizes that, then what one needs to do in order to give a deflationary interpretation of the thermodynamic limit here is to study the behavior on the way to the thermodynamic limit and on the way to the infinite iteration limit. And I think that if one does that, one has arguments coming from the topological framework defined by Wilson and Kogut, and also from computer simulations, to defend the idea that the behavior that is observed at the limits can be recovered by the behavior on the way to these two limits, which was what I defended in this paper. So even in this case, in which we have different limits going on, there is a possibility of giving a deflationary interpretation of the limit. So now last point is that I just said that for me, infinite limits here are not essential for an explanation of universality, but it seems that some coarse graining procedure, it is essential for the explanation of universality. It seems that if we have a model where we add too many details, we will not be able to explain universality, and we will not be able to explain the commonality, the common behavior among disparate systems. But this sense in which a coarse graining procedure is essential is again uncontroversial for the scientific realist, because the scientific realist in general accepts that abstract descriptions can be essential to explain common behavior among disparate phenomena. So, and again, I think here one can potentially have a nice notion of approximate truth, because in renormalization group methods, in principle, it is possible to compare the coupling constants that appear in the fine-grained model with the coupling constants appearing in the coarse-grained model. So we can try to quantify approximate truth, again, here following the definition of Chakravarti. And now, finally, the conclusion. So I said that in this paper, there was one main question, which was whether infinite limits are compatible with scientific realism. So the answer that I gave to this question is that, well, it depends on how the limit is used. If the limit is used as an approximation without idealization, then this is no problem for the scientific realist, because there is no paradox that arises, because the infinite idealization is not well defined, or it doesn't recover empirically correct results. If an infinite limit is used as idealizations yielding approximations, then there is no paradox, because one can recover the empirically correct result in finite systems, which means that the infinite system is not essential. In the case of essential idealizations, there is no paradox, but only if one can give a deflationary interpretation of the use of the infinite limit. And this depends on the case study. And as I said, there's no standard recipe to give a deflationary interpretation of the limit. And finally, if infinite limits are used as abstractions, there is no paradox per se, since they don't involve misrepresentations, but we can fall into a paradox if abstractions are combined with essential idealizations, which is the case of continuous phase transitions. But even in those cases in which there are different limits, we can still try to give a deflationary interpretation of the different limits. And that's all what I have to say. So, thank you.
Thanks so much, Patricia. We'll take a 5-minute break. Maybe we'll just come back at 12:30 to make it easier. Is 3 minutes okay? Okay, cool.
Yes,
So
yes.